So here's question 1 on the assignment. Water's flowing through this pipe and it's got this bullet-shaped thing blocking the end. The result is that the water that was going 7 meters per second here is going faster out through this annulus around that bullet-shaped block. The water has a density of about 1,000 kilograms per cubic meter. The velocity at location 1 here is 7 meters per second. So by continuity, the area ratio tells us how much the velocity increases. So V2 is A1 over A2 times V1. Punching that through, noticing that the area of this annular section, that's the space that's shaped like that, is pi times d squared, the large diameter, so 0.05 squared over 4, minus pi times d squared, the small diameter. That's the area of this section here. So the difference between those two is the area of the annulus. That's a trick that caught a few people. That gives us the velocity at location 2 is 19.44 meters per second. We're neglecting elevation in here, so from Bernoulli, we just get a variation in pressure that depends on the variation in velocity. This is just a rearrangement of Bernoulli's equation. So that the difference in pressure is density times the difference in the squares of the velocities divided by 2. And that gives me 1.64 times 10 to the 5th pascals, 1.64 bar, about 1.5 atmospheres. So the next question we want to figure out, that's going to be the reading on this pressure gauge, if this is atmospheric pressure out here. Next thing we'd like to figure out is how much force is acting to hold that bullet-shaped thing in place. So steady flow, control volume surrounding the entire system, and using gauge pressures, so the only pressure force is going to be on the inside here. We have the sum of the forces acting in the x direction equal to the difference between the momentum flow out of the control volume minus the momentum flow into the control volume. So if this is bigger than that, then we had to have a force applied in the positive x direction. So those forces are going to be P1 times A1. This is A1, pressure acts over that area. F acts in the negative x direction, so it's negative, and that's going to be equal to the mass flow. Well, the mass flow here and here are the same. It's steady. What comes in here goes out there. And this is the easy one to calculate. That's just rho times V1 times A1, the volumetric flow rate times the density. So there's m dot, and it's the same in both cases. Then V2, that's the U value at the outlet, and V1, that's the U value at the inlet. And it's negative because of the negative sign here. Punching in the numbers, and out comes 151.4 newtons. That's equivalent to the force of about 15 kilograms under acceleration due to gravity. So that's a fairly sizable force. You'd have to push reasonably hard on here to hold that bullet in there. And so, basic momentum balance question, fairly straightforward.